In the last video, you introduced phasors and went over some key characteristics about them. And now we're going to use the concept of phasors and specifically apply them to calculate the input impedance of a given circuit. And we'll also examine what happens to the input impedance when your load is an open or short circuit. At the end of this video, you should be able to understand and see that our basic relationship between the voltage and the current for a forward and backward propagating wave are still the same as what we were familiar with in the past, which is nice. The other thing is to be able to find the input impedance, specifically, which refers to the impedance that the voltage source would see on the left side of the transmission line if I gave you the characteristic impedance of the transmission line as well as the load impedance. And finally, once we've calculated this Z-in, we're going to look at the interesting things that happen when your load impedance is either an open or short. Now remember, way back in the beginning of the semester, we started everything by analyzing a very short segment of transmission line. And we modeled it with the equivalent circuit that you see here, with a series inductance and a shunt capacitance. In addition, if there's loss in the transmission line, you could quantify that in terms of a series resistor and a shunt resistor. In this case, remember that G is the equivalent of 1 over the resistor. And the main reason we're using G, the transconductance, instead of the resistance is that for simpler math, we want to just say that in the case of lossless transmission lines, the quantities of interest go to 0. So in this case, if this transmission line was lossless, we can model that by setting R equal to 0. And in the case of lossless over here, we really want this to be open. And an open circuit, instead of saying R goes to infinity, it's easier to just use the transconductance term, because then we can say G equals 0 to signify an open circuit. From this model, we developed and derived this transmission line equation that you see here. And if this wasn't lossless, we would have a minus Ri here and a minus GV here. But in this case, we're going to limit ourselves to a lossless transmission line for simplification, so these two terms go away. The new thing that we want to do is to see what happens if we limit our inputs to sinusoid signals of a specific frequency. What that means is that our voltages and our currents all take this form. So right now I have voltage written here, but you can also change this V plus to an I plus to signify a current, or a V minus to signify a reverse going wave. But basically we're still talking about a constant. We have an e to the j omega term and an e to the minus j beta z. What does that do when we plug that into the transmission line equation? You see that over here, the main operation is a derivative with respect to t. So what we can do is, if we take a closer look at what happens if you take the derivative of this quantity with respect to t, we get j omega v plus e to the j omega t e to the minus j beta z, which means that we get the original but multiplied by a j omega. Therefore, when we're limiting ourselves to sinusoids, we can state that a derivative with respect to t is the same as multiplying it by j omega. Therefore, our lossless transmission line equations can be simplified into this here. And in this term, there's the loss still incorporated in there. But again, we're setting this equal to 0. So we have our transmission line equations that now look like this. I'll rewrite this here for the lossless case, where we don't worry about the R and the G. Otherwise, this equation here is the same as what you were seeing before. Now let's plug in a generic forward and reverse going wave in the form of phasors. So again, phasors just means that we take out the e to the j omega t portion. And we'll plug it in here to see what the corresponding currents will look like. And if you go through the math, you plug it in, and you'll find out that if you put in this v of z, your I of z is going to look like this equation here, where the amplitude is scaled by z naught. And remember, you have a sign difference to correspond with the change in direction. But otherwise, the z naught still has the same definition as before. And our beta also, our propagation constant also has the same definition because we defined it that way when we were setting up our voltage equation. But you'll see that very reassuringly, the relationship between the voltage and the current stays the same as before. And in this case, we're still keeping it in generic terms. So you have a forward going wave and a reverse going wave and the corresponding forward going current and reverse going current. Still looks very much the same as what it looked like before. Now going back into our transmission line equation, we now have our expression for the voltage and current for any given location from the previous slide, and we had defined z equals 0 as the beginning of the transmission line and z equals L at the end of the transmission line. Now let's start by taking in our equation and try to find an expression for the voltage and the current at the load. To do so, all you have to do is take our expression from the previous slide and plug in V of L and I of L. So all we're doing here is we're setting Z equal to L in our previous expression in the last slide. So what that gives you is a very similar equation as what we had at the end of the last slide. Again, all you're doing is you're setting Z equals L in the various locations, there, as well as here and here. And you can see that our Ohm's law relation still holds, where the current, we set that, therefore we are able to set in the restriction that the current is going to be the voltage at the load divided by the load impedance. Let's take a look at this again, and what we have is actually, if we set this equal to VL, because again our definition was this is the equation for the voltage at the load, once you apply these restrictions you have a system of two equations and two unknowns. So if you take this and solve for V plus, the forward and backward propagating voltage wave, in terms of the voltage at the load, and do some reorganization, you actually can end up with this expression here for the forward and reverse voltage as a function of the load voltage and the impedances that are involved at the load end. Now, with this result of V plus and V minus, what we want to do is plug this back into the V of Z and I of Z, so not the Z equals L, but the general version of the voltage and the current anywhere. As a quick review, at the end of what we had earlier, we had this general expression that we found from the transmission line equation of e to the minus j beta z, and the reverse wave e to the j beta z, and we had our current which is the same but scaled by z naught, and there's a minus sign difference for the reverse going wave. This should be plus to signify that it's a reverse wave. So what we're going to do is we're going to plug the V0 plus and the V0 minus in here to get an expression for V of z and I of z. Once we plug all that in, we can come up with an expression for the impedance by dividing the two. Once you plug all that in, naturally you get a big mess, but you can kind of see where things come from. With our last V plus and V minus equations, we still have the VL/2 that's still there, and also the 1 plus Z0/ZL. The main difference that you see here is because in the original equation recall we had a J beta Z term that we were multiplying in, and that along with our original J beta L that we got from the last slide gives us this quantity here. So you can plug it in and try it out yourself, but the algebra works and you end up with this messy form here. And the important thing is that one of our big unknowns in this equation, VL, actually can cancel out. And what that leaves you is an expression for the impedance experienced by the wave at any point in terms of all known quantities, because we know what the transmission line impedance is, we know what the load impedance is, and we know what the length of the line is. Therefore, we now have this expression for the impedance experienced by the wave everywhere. Now, if you go through a bunch of more algebra by first applying Euler's rule to convert this into cosines and sines. So remember, you change E to the J theta as cosine theta plus J sine theta. You apply that to all of the exponents and here and do a lot of simplifications, also using the fact that the tangent of theta is equal to the sine theta divided by the cosine of theta. With some work, you will end up with this slightly prettier expression here for the impedance at any location z. So what this gives you is for our transmission line equation, where we had our impedance and then a transmission line with ZL and a transmission line of Z0. Z of Z gives you, this is Z equals 0, Z equals L. Z of Z tells you what the impedance is experienced by the wave at any given location along the transmission line. Next up, if our goal is to find out what is the impedance experienced by the generator, what we would want to do is find out what Z of Z is at the input. So you can imagine the next step of what we want to do is substitute in Z equals 0. Again, in the last slide, we have our expression here for Z, which is the impedance experienced by the wave at any point in the transmission line. Now to find the input impedance, all we'll do is we'll set Z equals to 0, which allows us to evaluate the impedance at this point. If you do that, then you can see we just set little z equal to 0 here, and we end up with this expression here for the input impedance. What that means is before, when we had this original transmission line here and we had a function for Z of Z, by plugging in Z of 0, you get the input impedance, which means that we can just model everything that's to the right of this boundary that I drew here with a single impedance Z in, which is what gives us this drawing over here, where now we just have the generator with its input impedance, and we're just hooking it up to a single impedance that's characterized by the equation that we just found. Next up, we'll look at some special cases of what the input impedance will look like if ZL is either an open circuit or short circuit. Let's start with the short circuit situation. Again, we have our general equation here for Z input. If the load is a short circuit, then what we're essentially doing is we're setting ZL equals to 0. So if we rewrite that, we'll have Zn is equal to Z0, and then inside we have 0 because this goes away and this goes away. So this whole term goes away, and we're left with, let's just go straight to J Z0 tan beta L all over Z0. These two terms cancel, and you're left with this expression over here, which is just a nice little trigonometric expression, the tangent, which we maybe aren't as familiar with plotting compared to sines and cosines, but that knowledge hopefully is buried deep in our brain somewhere. As a quick review, let's plot it and see what it looks like. Over here, in this plot here, we have, as a function of the length of the circuit, we will plot the input impedance. Now, I'm changing the letter Z to X because there is no real part. It's purely imaginary. And therefore, since the impedance is only imaginary, we can get away with just plotting the reactance. As a quick review, I'll just mention quickly that reactance is imaginary impedance, where the impedance just has the imaginary component, and when it's greater than 0, you can create this either by using an inductor or capacitor, since the impedance of an inductor is j omega L, and the impedance of a capacitor is 1 over j omega C, which is because 1 over j is equal to minus j, is equivalent of negative j omega C. So you can model a positive imaginary impedance and a negative imaginary impedance by using an inductor or capacitor. Therefore, in the regions where the reactance is greater than 0, it's an inductive load. If it's less than 0, it's a capacitor load. So now that we declare that we're plotting in terms of reactance, which by definition is just purely imaginary, that means that in our expression for Zn, we don't have to worry about this j anymore. And we're simply plotting this term here, which is a tangent. So if we pull out our calculators or in MATLAB or Google tangent and look for images, whatever you need, you'll recall that a tangent looks like this plot that you see here, where at lambda over 4 and 3 lambda over 4, you have this asymptote. And between lambda over 4 and 3 lambda over 4, it has a curve like this here. The neat thing about this result is that the range of the reactance actually goes from minus infinity to infinity, meaning that you can simulate with a transmission line ending with a short circuit. You can essentially create an input impedance equal to any reactance just by adjusting the length of the transmission line as a function of the wavelength. So let's look at some characteristics. So the reactance goes to infinity at lambda over 4 when you're approaching from the negative side. Let's see, we have 3 lambda over 4 when approaching from the negative side, but basically every odd multiple divided by 4 every odd multiple of lambda approach from the negative side. It equals negative infinity over here when for those same numbers but approach from the positive side. So again, any odd number divided by 4 of lambda approach from the positive side. And when it's infinity, basically means that it's mimicking an open circuit. And also, we'll note that there are nulls at lambda over 2. There's going to be another one at lambda, but it will be equal to 0 at lambda over 2, lambda, 3 lambda over 2, but basically any even multiple of lambda over 4, which is the same as saying every multiple of lambda over 2. You will get a reactance equal to 0, which means that it behaves as a short circuit. Now let's look at the other situation when the load is an open circuit. Now to do that, that's the equivalent of taking the limit of the load goes to infinity. And that means that this term and this term will dominate. And if you apply L'Hopital's rule, or general knowledge about limits, you'll know that the limit of this fraction here is going to be the ratio of the coefficient of this ZL and the coefficient of this ZL. So we have our Z0 from here and 1 over J tangent beta L. Now if we remember that 1 over J is equal to minus J, and also that 1 over the tangent is equal to the cotangent of theta, you end up with this expression here. Again, it's similar to what we had before, and all we have to do next step is to figure out what the cotangent looks like, which you can do by doing a quick calculator plot, or again going to Google Images and looking at cotangent, and you should be able to draw something that looks like this. Again, the possible ranges of the reactance that we can get, the equivalent input reactance, still spans the whole gamut from negative infinity to infinity. And so again, with an open circuit like a short circuit, you can mimic any reactance value by controlling the length of the transmission line. Let's write out, as the last step, let's write out the key characteristics compared to what we had before in the short circuit. The input reactance will go to infinity at lambda over 2 approaching from the negative side here, lambda approaching from the negative sign, but essentially any even multiple of lambda over 4, which is the same as any integer multiple of lambda over 2, times lambda approaching from the negative side. And it will be negative lambda when you approach these same values from the plus side. So we'll say n over 2 lambda from the plus side. And these two, since they're infinity, basically means that we have it's mimicking an open circuit. And also, we'll see that it equals 0 at lambda over 4, and you'll see at 3 lambda over 4. So lambda over 4, 3 lambda over 4, but essentially any odd multiple of lambda over 4, which means that at these locations it will mimic exactly a short. So we have the same situation where it can be an open or short, but the question of whether this occurs at an even multiple of lambda over 4 or an odd multiple of lambda over 4 is flipped when you're talking about an open circuit versus a short circuit. So using this little characteristic, you can see that multiples of lambda over 4 is a little bit of a magical length. And next time we'll talk about what we can do with certain stubs that are a length of multiple of lambda over 4. To summarize, we went through a little bit of math, revisited the transmission line equations, but from the perspective of inputting phasors, which allowed us to do certain simplifications. And again, the introduction of phasors just means we are limiting our scenarios to when the input is a sinusoidal wave, so something that looks like this form of a singular frequency. Using that, our ultimate goal was to derive what the input impedance looks like, which is the impedance that the generator sees. And then we saw some interesting things happen when the load impedance is an open or short circuit. Specifically, we saw that it can mimic any reactance, but it also has ability to make the generator see either an open or short circuit. We also noticed that magical things happen when the length of the transmission line that's terminated by an open or short circuit is a multiple of lambda over 4. So next time we'll look more into what kind of things we can do with this lambda over 4 multiple. This quarter wavelength characteristic is pretty important because it gives us one of the basic techniques that we have for impedance matching for sinusoidal signals, which we'll learn about in the next few lectures.